In the mean estimation problem, given a function f mapping omega onto the real numbers and a probability distribution pi over omega, we estimate the expectation over pi of f by taking enough independently and identically distributed samples from pi. Using standard methods such as Bernstein bound, the sample complexity of mean estimation depends on capital V, a known upper bound on the variance V pi.
When IID sampling is not possible, we often use the Markov chain Monte Carlo method. In the Markov chain Monte Carlo method, we run a Markov chain for capital T number of steps when capital T is a known upper bound on the relaxation time to collect one sample. We call this a trace of the Markov chain. To collect more and more samples, we need more and more traces. The sample complexity of the standard MCMC methods is tilde O of capital T, capital V. Remember that capital T is a known upper bound on the relaxation time, and capital V is a known upper bound on the variance of F. We now ask the following question. In order to take multiple samples, we need multiple traces, each corresponding to one single sample. Is there any information in these traces that we could use to design more efficient MCMC mean estimators?
In this paper, we answer positively to this question by introducing trace variance. In standard methods, we collect a sample after running an entire trace. In our method, we instead average the function over the entire trace to collect our first sample. Again, we average the function over the second trace to collect the second sample, and we average the function over the third trace to collect the third sample. The trace variance is then the variance of the average over traces.
We now ask the following question. What is the relationship between trace variance and the stationary variance? If the length of the trace T is at least relaxation time, we know that the trace variance is smaller than the stationary variance. So any algorithm whose complexity depends on the trace variance would be at least as good as the standard methods. So we ask a more interesting question. Assume that the length of the trace is equal to the relaxation time. When do we have that the trace variance is significantly smaller than the stationary variance? We believe this occurs a lot. In particular, it occurs when the image of F projects on the Markov chain and it makes it a simpler chain. For example, consider F, which is the mod 2 function, and the Markov chain, which is a cycle. The image of F on these traces is so symmetric that the projection chain will be a very simple two-state chain. The relaxation time for this chain is very small, so the trace variance will be significantly smaller than the stationary variance. We show more interesting examples when the trace variance is small in our paper.
The Dynamite algorithm leverages the idea of trace variance to estimate the mean. We take as input capital T, a bound on the relaxation time, and f, the function whose mean we are trying to estimate. To start, we run the chain for capital T steps. We then compute the mean and trace variance. We then check the termination condition. If we are done, we return the mean. Otherwise, we double the sample size and repeat. The sample complexity of Dynamite is O tilde of the trace variance times the relaxation time. Compare this to standard methods, which get O tilde of an upper bound V on the stationary variance times an upper bound T on the relaxation time. These standard methods not only have worse sample complexity, but also require a priori knowledge of capital V as an input to the algorithm.
Note that Dynamite does not need any information about the trace variance. However, its sample complexity is dependent on the trace variance. It simply runs the Markov chain and it automatically stops faster when the trace variance of the function on the Markov chain is smaller.
To summarize, the trace variance better characterizes the sample complexity of mean estimation than does the stationary variance. For example, if we want to calculate the mean distance of a random walk to the lake, we run our Markov chain and collect samples. Standard methods would only be able to use every 5 samples, x0, x5, x10, 15, 20, and 25. However, with our method, we average over each column, which is a trace of length 5, and using all of this information in the average, we get a better sample complexity for the mean estimation problem.
If you are interested to know more about our techniques, please read our paper.